Shashwata, and all my dear children. On behalf of KV IIT Guwahati, I take this privilege to welcome Uddipta and Shashwata for this enlightening session on beautiful topics in the world of physics. Personally, if you ask me, coming from a biology background or like studied biotechnology, for me, physics is something like, it's a gray area. I wouldn't, venture more to talk about things in physics, but it's something that has always fascinated me. And probably if I had somebody like what, you guys are getting today, like we had Uddipta, probably, or some teacher who could have enlightened me in this physics, probably I would have opted for that. So I request all of you to seize this opportunity to understand, comprehend, reach out, and make the best use of what is available today. To talk a little bit about Uddipta, of course, gives great pride, when I talk about him, because he was one of my favorite students. He matriculated from Kendriya Vidyalaya Khanapara in 2013. He went to Delhi University for his bachelor's with honors in physics as an Inspire Scholar. Very few students get this Inspire Fellowship, and Uddipta was one of the first one who got it from KVK. I'm very proud of him for that. And during his bachelor's, he carried out research in radio astrophysics at the National Center for Radio Astrophysics, India, and furthermore at IUCAA and UT Radio Telescope, India. He worked as a research assistant at ISRO for 6 months in 2017 on a project involving black holes. In 2018, he moved to Heidelberg University in Germany as a DAT scholar and carried out research on cosmology and dark matter using galaxy clusters. In 2020, he moved to GRAPPA at the University of Amsterdam as a Cortex scholar, where he is doing his PhD research on gravitational wave sources funded by NVVO grant. He is a member of Cortex Collaboration, LISA Consortium, and an external student member of Euclid Consortium. I am sure that most of you will be using many of these terms as as I am feeling right now, because for me, I just understand that these are all huge achievements. And for me personally, I would say that his greatest achievement is the fact that he wants to uplift students. He wants them to come up to, their highest potential and do well in the field of research. So this venture of him, along with his friend, is, I would say that it is a great act as a research scholar and as a person who is pursuing physics. So thank you, Uddipta. Thank you, Shashwata. The floor is all yours. Thank you.
Thank you. Thank you. That was a very long introduction. Great one. Yeah, well, I'll start with thanking Ramam actually first, because she was the one who showed initiative to get me connected to you students. And she was actually the first person who motivated me to do scientific research when I was very young in school. So that's kind of great. That's how I ended up here actually. I'm joined today by my friend Sashwat Hussain from Heidelberg University in Germany. He's a master student there. He's doing he's finishing his master thesis now, and he works on quantum gravity. I myself am at Amsterdam. I am employed by the University of Amsterdam, and I'm a GRAPPA fellow, and I work on radio counterparts of gravitational wave sources. So first of all, why I'm doing this is basically because it's a personal venture of mine, this public outreach. I'm not funded by the university or any other association to do this. I do this at my own will, and just because I feel that connection to you students. I could only hope that we would have received this kind of outreach ventures from people across the world. But nevertheless, there's never a right time to start. So this is the best time to begin this. So what we are going to talk about today is an astrophysical entity called pulsars, and how we'll talk a little bit about what pulsars are, when they were discovered first, and there was a crazy furor about them being aliens from outer space. So me being an astrophysicist, I do have to deal with the very frequent question of say a non-astrophysics or non-scientific person, which goes along the lines of have you dealt with aliens, or do you think that intelligent life exists outside of Earth? So so this talk would deal with questions of that sort. All right, so I'll try and share my screen now, and I hope you can see it. Share. Okay, is my screen visible?
Yes, Sudeep.
Okay.
It's visible.
All right, so once again, welcome to all the students. I'd like to say that this is, although this is a scientific talk, this is a very basic talk. This is something that I did about 6 years ago on a project. I'll keep it very informal, very basic. It's a small group, so this is very nice. You are encouraged to ask any number of questions that you want. The talk will be very short, but the question answer session can go on as long as you want. Ask any questions. It can be regarding the talk, related to the talk, related to me, related to science, anything at all, related to career opportunities, any question at all, whatever you want. So without further delay, let's start this talk. This talk is titled Little Green Men, and it's about aliens in astrophysics. So whenever we come across the word aliens, we are constantly reminded of a humanoid entity who looks usually green, as we see in Hollywood movies about Area 51 and stuff like that. So it usually looks something like that, where most of the alien visualizations in movies and stuff are usually little green men. So this is something that any layperson would have in their mind when they talk about aliens. But what were the first instance of such an alien being seen or being asked about to an astrophysicist? Let's see. Let's look at it. So today we are going to talk about pulsars and how we can connect them to aliens. Let's just see. So what is a pulsar? It's an astrophysical entity. And when you look at the night sky, if you see a head-on pulsar, it just looks at a flickering. It just looks like a flickering star or a pulsating star. It looks something like this. So it pulsates and it flickers. It has periodic increases of its brightness, and then it dims again. But they have the time variability of the pulses are usually from about a millisecond to about 9 to 10 seconds. So very fast pulsars to very slow pulsars. What they actually are that they are not pulsating stars. So they don't really change their brightnesses or their luminosities. They don't really do that. They don't really pulsate. What actually happens is something called the astrophysical lighthouse effect. So this lighthouse effect, what pulsars actually are, is explained by something which is called a neutron star. So a neutron star is actually a dead star. It's the fate of a star. So a star, depending on how big it is, say for example our sun, or how big it is, ends up in different fates when its life cycle ends. When we talk about life of a star, we basically talk about the engine of the star, so the nuclear fusion that's our sun is not big enough, unfortunately, or fortunately, to be a neutron star. But this is one of the fates, and another very popular fate of a star is a black hole, right? These pulsars are actually highly magnetized neutron stars. You can see the magnetic field lines here, and from the magnetic poles, usually there's continuous and beamed emission. So the emission, the brightness is not really flickering or pulsating, it's continuous and it's beamed. So what you see is that it's rotating. So what happens is that the beam comes towards us. You see something bright and then it dims again. Once again, it comes towards us. You can see that it gets brighter and then it dims again. So what basically happens is that using the pulse profiling or the timing of the pulses, we can find out information about the rotational velocity of the star and stuff like that, right? Okay. So let's take a look at what was the first pulsar and when was it discovered. So when we talk about pulsars, we always have to give credit to this person here. She's one of my scientific heroes. She's Dame Jocelyn Bell Burnell, and she discovered the first pulsar when she was actually a PhD scholar at the Jodrell Bank University, Jodrell Bank Observatory in England. The first pulsar was detected in the 28th of November, 1967 in radio astrophysical data. It was called B1919 plus 21. This is a kind of nomenclature for pulsars. So this is what it was called. And also at that time, it was called LGM1. Why LGM1? Because then LGM stands for basically Little Green Man 1. At that time, in 1967, there was no really, not really a concrete physical attribution to any known astrophysical source. So they could not attribute that the pulsar is actually a neutron star or something like that. This is new information. They didn't know that at that time. So what they thought, the media and the government, they thought that there were aliens or intelligent life outside our Earth who are sending us signals in pulses like Morse code or something like that. So they thought that little green men from space, so the media publications during those times publicized pulsars as little green men sending us signals or pulses. In 1974, the Nobel Prize for the detection of the first pulsar was awarded to Sir Anthony Hewish. Sir Anthony Hewish, Professor Anthony Hewish was the PhD supervisor of Dame Jocelyn Bell Burnell. And unfortunately, Dame Jocelyn Bell Burnell was not recognized for her work here. As at those times, being a woman in science was difficult, and she was not the first author of the research paper that they published. So Sir Anthony Hewish got the award. Nevertheless, so this was something like a media article that that was published in 1968, and you can see they're talking about little green men here. And this on the right, you can see the image of the observation log of the first pulsar. So you can see the radio continuum, and then you can see the pulses here, the absorption lines, and you can see the fluctuations. So the fluctuations represent increases and decreases in brightness. So this is how they imagine pulsars to be at that time. So aliens sending us signals from a very highly magnetized entity, right? But later on, we know that this is not the case. So what actually are pulsars? Let's look at this short video to try and understand what they are. So it says it's a rapidly rotating high density neutron star. So here what they have done is they have taken the frequency of the pulses and they moved it to an audible frequency, shifted it to an audible frequency to see how it looks like. So you can see the different pulse times. So this is just to give you an idea of how they behave, basically. So,
Uddipta, just a second.
yes.
For some reason, I think you've given access to screen to other people, and I can see marks on the screen.
I haven't really, but if someone's doing that, then we can remove them, log the meeting. That should be all right.
I mean, please don't do this kind of thing. I mean, it's a nuisance, and I mean, I don't want to take names, but I know
Yeah, because the names are showing here basically.
because names are showing here. Please don't do this.
But it's all right. It's all right. We can continue. That's just a minor
Sure.
thing. Okay. So the pulsar that we are, so this part of the talk, I'm going to talk about a pulsar that I studied. This was way back about 5 or 6 years ago. So the pulsar I studied, and then I did a little bit of an experiment with it, which I want to share with you guys, just to give an idea of what kind of research you can do with pulsars at a very basic level, right? So the source of interest is known as B0329 plus 54. This is the name of the pulsar, as you can see from the naming convention. The RA and dec are right ascension and declination. These are coordinate values. You can imagine right ascension to be kind of like an X coordinate and the declination to be an Y coordinate. If you imagine in Cartesian systems, these are celestial coordinates, in fact. And then this is the pulse period. So this gives you the periodization of the pulses, which is about 0.7 seconds. And then distance to a pulsar is usually estimated using various methods. One of the methods of direct estimation to the distance is using parallax, something we call parallax. You observe it from a certain position, you observe it from another position, and then you see the difference in the lengths, and then you use the use trigonometry to kind of measure it. That's a direct method, but it's very extensive, and it requires a lot of infrastructure because you need 2 telescopes at 2 different positions and everything. So what I did in this experiment is try to find the distance to the pulsar using a very indirect method, which does not use a lot of infrastructure, but only a single observation of a pulsar. It has a radioluminosity of 1500 millijanskis per kiloparsec square. It's just an estimate of how bright the pulsar usually is, so that you know whether your telescope has the required sensitivity to detect it or not, right? Let's take a look at it. So this is how the pulse profile usually looks like. You can see here the pulses. You can see here the waves, the pulses. These peaks represent the pulse, the bright pulse, and then the troughs here represent like the dimming. You can see it's very noisy, of course, because the pulse has to pass through a lot of interstellar medium, intergalactic medium to reach us. And as we know that it doesn't really travel through a vacuum as we usually study. If it was the very ideal case, then we would see a perfect peaks and a perfect line as the continuum. That is usually not the case, so you have to clean the data a lot. This is an observation that I did myself using the OT radio telescope. This was done over a time period of 15 minutes, which is about 900 seconds here. And we already know that it should contain about 1,000 or a bit more pulses because the pulse period was about 0.7 seconds, right? Now, this is the frequency shifted pulse profile of the same pulsar. You can see how it sounds like. It's the same plot, but with the frequency shifted to an audible range for us so that we can understand it better by hearing it. Now, the pulses that come from the pulsar to us, again, are affected by dispersion, scintillation, scattering. These are all effects that are caused because of density variations along the line of sight. You must have studied in your classes about refraction and all these things, dispersion, reflection, and refraction, and all these things. These are optical effects. The dispersion measure provides us an estimate of how about the degree of dispersion that the pulse coming from the pulsar to us experiences. This is provided by the dispersion measure, which can be calculated again by this equation. This gives us something, the DL, integration DL gives us the length from us to the pulsar. And the NE here is the number electron density actually. So this is the number density of the electrons in the media along the line of sight. And this number density determines how much dispersion the pulse has to endure. We also know that this is how we calculate the refractive index. So we know how much it will get refracted. And then because of dispersion, there's a time delay. The time delay is basically calculated by the time the pulse would reach us if there was no dispersion. So if there was a vacuum, and then the pulse arrives from the pulsar to us, which is dependent only on the light speed in vacuum. But what happens is that we get it a bit later. So there's a delay in the pulse arrival time. Why do we get it a bit later? Because of these effects, right? So the delta t, the time delay, can be measured using this formula where you can simplify it to a constant times a function of the frequencies involved, and then dispersion measure. These are observation frequencies so you need like different frequencies to observe the pulsar in, and then you can calculate the time delay. You can get an estimate for the time delay. Now, this is a very economical and indirect way of distance estimation. If we can find out information about the time delay, the frequencies, and the dispersion measure, or the time delay and the frequencies, you can calculate using this formula the dispersion measure, and then you can use it here in the above equation to calculate the distance if you know the number electron density. Now, it relies mostly on source and medium properties rather than a lot of infrastructure. So what we did, since we did not have a lot of frequencies to work with, we did not have multiple telescopes to work with, we used the full bandwidth of the UT radio telescope, which is about 16 megahertz. Now, we used the 16 megahertz bandwidth and split it into 8 bins. So how we split it is we took 2 megahertz bins of equal width and we split it into 8 parts. That's basically what it is. And we observed the pulsar in all the 8 bins. What that does is that gives us different values for the frequency and the observation time at different frequencies. Now we have from the previous equation values of F1, F2, and more if we want, and also the time delay, because we observe it at a certain time and then at a different time at a different frequency, which is evident from these. You can see the peaks here are shifting a bit. This is the first bin, and then you can see that it's shifted a bit here, and then on the third one a bit more, and it gets closer and closer. It shifts towards the right in the image. These are the 8 bins where it gets shifted more and more. You can see it's getting beyond 200 here. So these are kind of arbitrary units for the bins, and I'll show you how they translate to time. So what we do is we tabulate what the peak position of the frequency peak, the amplitude peaks are, and the frequency bin in which we are observing it in. This is the 2 megahertz frequency range, and we are using the central frequency of that bin. So if it is 1 to 3, 1 megahertz to 3 megahertz, we are using the 2 megahertz central frequency. So these are the 8 central frequencies, and these are the peak positions, which we get from this plot. We just check what the peak position is, and we check which frequency band this is. Now we can change this, we can convert this peak position column to something which is called pulse arrival time. So which will give us information about what delay we are experiencing in observing the pulsar. This we can do is by, how we can do this is we take the pulse period and then multiply that by the peak position by the total number of bins. Peak position divided by the total number of bins, and we multiply that by the pulse period, which we already know, which gives us a pulse arrival time in milliseconds, which you can see here. These are the values of the pulse arrival time in milliseconds, and then the frequency. So you can see that it's getting delayed as we go higher in frequency. The arrival time is increasing every time, right? So now we have information about the time delay, which we can calculate just by subtracting any 2 of these. And we also have the different frequency ranges. So we have F1, F2, F3, all these things till F8, and we also have different time values. So from that equation, it's easy for us now to calculate the dispersion measure, right? Now, if we get the dispersion measure, what we are actually interested in is the distance. And for that, we need another quantity, which is called the number electron density of the surrounding media. For that, there are different models, theoretical models that people develop using mathematical modeling, numerical modeling, and techniques like that. They kind of try and simulate it in a vacuum, and then they add different properties, physical properties to it to make the model as realistic as possible. There are different mathematical functions that can very well describe density variations in the environment. And I really don't want to go into too much detail about this, because this will get really beyond the scope of this lecture. But usually what we did for us was we used an electron density model called the YMW16 electron density model. It was developed by Aaron Manchester from CSIR Australia. and it was constructed as usual using radial plus angular variation functions. So that's it's kind of like a computer program where you can input the source position and stuff like that, and it will give you the density variations from you to the source the source location that you have provided. Not really the variations, but the number electron density, which will give you further information about the variations. Now, what we did to calculate the distance was we plotted the pulse arrival times that we had before and the frequencies. So what we did basically was plot this table. This gave us information about different frequencies and how the pulse arrival time is increasing. It should usually be a straight line, but obviously there are observational inaccuracies that you have to endure. So you get something which is kind of like a straight line. It just fit to a straight line. The green line is the straight line, and then the red line is what we observed. Now, the slope of these curves provides us information about the time delay, delta t, and delta f. You can subtract any two of these and any two of these as well. Now, these values can be used in this equation to have an estimate for delta t. We have delta t, we have f1 and f2 values, so that gives us the dm, right? The dispersion measure. Once we get the dispersion measure, which was about 27.856 centimeter per centimeter cube parsec, parsec is a unit of distance, we can calculate the distance, where all we need now is the number electron density, which we use from the model that I just told you about, the YMW16 electron density model. So we put input here a value of the electron density, we get an estimate for the dispersion measure, and then we get the distance to be about 0.99 kiloparsecs. Now, you remember in the beginning, we had the distance of the pulsar estimated from direct methods like parallax, and it was cataloged to be at 1 kiloparsec. So we can see that this method of estimating distances is quite accurate, so which was nice. So that's basically the end of the technical part of the talk. I have to give credit to Dame Jocelyn Bell Burnell for her incredible achievements, for discovering the first pulsar and everything. I have to give credit to the National Center of Radio Astrophysics and the UT Radio Telescope in India, where I did a bit of work on this. And these are some of the resources that I used to write this. I have to say that usually what happens in studies where these things are attributed to aliens and stuff like that, what usually happens is that when you think about aliens in that respect, we tend to kind of fall back on that option whenever we have some unexplained detection or unexplained study. So whenever we see, suppose, an astronomical source which is unexplained, we kind of tend to fall back on that option and attribute it to something like aliens, which makes our jobs easier, of course. But that should not be the case. We saw in the recent Venus studies where they attributed it to aliens very fast, where they studied phosphine absorption in Venus. But later on, we figured out that it might have been a data analysis error, but there are more studies going on, which again debunk these things. So yeah, these kind of things always go on. So we should be very careful about that. So here I come to the end of my talk. I'd like to thank you all. I encourage you to ask any kind of question possible. I was always that student who would ask any question at all. It can be related to the talk. It can be completely unrelated. Just ask away. Feel free to ask. And thank you.
By the way, that photo is taken by me.
Yes, photo credits Sashwata. That's true. All right. So I'm going to.
Thank you, Uddipta. Children, you can use this opportunity to ask any number of questions regarding even careers in physics, or if you have any doubts in physics, anything you can ask. Feel free to ask, please.
Anything at all, no problem.
Excuse me, can I ask a question?
Yes, please go ahead.
It's completely unrelated to the topic.
No worries.
So I want to ask that is it possible to, so is it possible to have something beyond universe?
something, sorry?
Means something beyond universe. Like we say that universe is the end. Like,
Oh,
is it possible to have something beyond universe?
okay. I think I'll let Shashwat answer that question.
I was about to say that I think this is my field. So, okay, so what do you mean by universe? I mean, like if I ask you, what do you mean by universe? The first question is, what do you mean by universe? So, I mean, you have to go a bit back to philosophy. So, what is meant to be science? Science means that we do some experiments and some verifiable facts, like we have some objective truths. For example, somebody said that, like, I mean, you guys are in 11, 12, so you might know. So a free fall body accelerates at 9.8 meter per second square. This is something Newton predicted. So you do an experiment on freely falling bodies and try to estimate this and confirm his fact. So this is, I mean, I will digress a little bit because this is what science is. So, so this is not a scientific question if what is beyond universe or not, because what we cannot observe, we cannot say anything about it. For example, like you say, okay, we have an observable universe. Outside the observable universe, there could be, I mean, it's a very absurd statement that there could be two flying penguins playing football with each other, and there is Zlatan Ibrahimovic is the referee, something like that. Nobody can verify that. You can say that, but nobody can verify that. It's not an unverifiable fact. So this question itself is not a very scientific question. I'm not saying that you asked a stupid question. I'm just saying that there's a distinction between, I mean, don't take it that way. What I mean to say, it's actually a good question, but there's a distinction between what is science and what is not. And is there any follow-up to this we want to ask?
So I'd like to say that I think Christy, right? So I'd like to say that's actually a very nice question. The thing is, whenever we talk about the universe, the notion that is in our mind is of the observable universe, right? So we have observations in astrophysics, and then we constrain mathematical models of what the universe can be like, or whatever the physics that defining the universe can be like. But then our observations can only reach so far. There are ranges that we cannot really exceed. So that's why when we talk about something beyond the universe, we can only kind of have mathematical models and ideas describing them, but it's not really, we cannot really solidly define what it can be. There are theories of the multiverse which say that there are multiple universes and ours is only a bubble, but we can't really say what is beyond that, right?
But I will add to it. You can say, but only if it has any observable effects on our observable universe. For example, if theory of multiverse is required for us to explain something which is going on in our universe, then we can say that multiverse is right. But you can have multiple models which are equivalent but has no effect on our observable universe. Then we can't say it's a scientific question. Again, I want to emphasize on that. It's a very, very good question. I just want to say that there's a distinction between some questions which are scientific, some questions which are not. It doesn't mean that the question itself is a bad one. It's beyond science.
So the quick answer is we don't know.
Thank you, sir.
We deal with only science.
Yeah.
So yeah, thank you, Christy. Thank you. Jagriti
Thank you,
has
sir.
asked, where is a pulsar located in the universe? So basically everywhere, actually. So it's just a star. It's a neutron star. So it's a star at the end of its life. So it can be basically everywhere. The real question is whether we can detect them or not, right? And that depends, again, as we saw, on several environmental effects. When I say environment, I talk about the environment starting from the pulsar to us. So you can't really have a favorable location to say that this is the location where we estimate that there could be pulsars, and in another there could be not. So there's nothing like that. They're everywhere in the universe. I'd like to encourage you to check the ATNF catalog. I'll write it in the chat. The ATNF catalog. So this is a pulsar catalog maintained by Australian Telescope National Facility, something like that. In the ATNF catalog, you can find information about different pulsars, and you can input, say, coordinate values, and you can see where they are and find information about pulsars. They catalog like thousands and thousands of pulsars. There are lots of them everywhere across. And if you they take the coordinates from each of the pulsars and plot it on a map, you'll see it, that it covers a huge part of the celestial map, right? Okay, Jagriti. Next is Ayushman. What is Area 51 and what? I wish I knew, Ayushman. I'm also trying to answer that same question. I wish the US government gave us information about what Area 51 is, but it's basically just a military testing facility as far as I know. Yeah. So more questions, please. It can be anything. Don't worry about the question. Just ask away.
Yeah, Ayushman seems to have one more question, Udi.
Yes, please. You can unmute yourself and talk. You can write in the chat, however you feel free. Just go ahead.
Uddipta.
Yes.
I am Haripad Das, Principal KV IIT Guwahati.
Oh, welcome, sir.
Thank you. I would like to request you to give some motivational speech for our students, so that they can be motivated, they can reach to the height they are capable of. Please.
I can't say that I'm good at motivational speeches, and I can only speak with clarity about something that I know and work on. But as far as motivation is concerned, I'll encourage everyone not to look for external motivation. Find the motivation within yourself. You can get inspired by people around you. You can get inspired by people that you admire, that you connect to, your teachers, your mentors, all these people. But the motivation that you need to really go ahead and achieve great things in your career always comes from within. It has to be from inside. And one thing that is even greater than motivation is something called discipline. So you need discipline in life. I'm not asking you to be an extremely studious person. I was never one. But just find some time of the day to dedicate to your studies. Also have a very, also really focus on your all-round development. Go for sports, extracurricular activities, everything. Don't really focus on exams and studies all the time. And if you have, there are times where you'll have sudden surges of motivation inside when you have something nice happen to you. And what happens usually is that motivation dies out after some time. So the only thing that carries on is the discipline that you have. And that's very important. It's not always, it's very easy to even start something, but people are wrong when they say that once you start something, everything else gets easier. It doesn't, in my opinion. You have to have that discipline inside you to keep going on. So always focus on being disciplined in your own way, of course, and try and focus on an all-round development. You should know which resources to use. Try and be very, how can you say, try and be open with your teachers, discuss a lot with them. If you're having any problems, talk to them. If you don't understand something, try and talk to them after your classes, get your concepts clear. Read very basic books. Those are the most important ones. You don't have to go into very technical details from the very beginning of your studies, not at all. Have the basics clear. I'll tell you, give you a short example of some of the most important chapters that I myself neglected when I was a kid, and that affected me a lot during my studies later on. One of them was units and measurements in physics. That was one of the first chapters, and that was the most neglected chapter because it seemed very easy. Actually, a very important chapter. Very, very important chapter.
I would just interrupt for a minute. It's an extremely important chapter, and this has I mean, this has a lot of consequence in what I am doing, and it's actually related to one of the most important problems in physics, is that how does gravity works in small scale. So please don't neglect this chapter.
Yeah.
This is important. The basics, it looks easy now. As you go on, it becomes a very valid and very open scientific question, especially for physicists.
That's true. And similar, another similar chapter is where they used to explain the forces, the different kinds of interactions, like the four forces and stuff like that. So these are some of the chapters that are really fundamental. And that's why I always say, keep your fundamentals straight and clear. Always interact with your teachers, ask them questions, share your problems with them, get information about stuff, and the rest will just fall into place. Have that discipline, and then you don't really need any other external motivation at all. Okay, so I'll look into another question.
I mean, for mathematics, I think everybody is CBSE here. So I would say for mathematics, please don't neglect set theory and relations and functions chapter, because this, in the it looks, because there are no problems, or it doesn't have a lot of weightage on board exams, or maybe JE or whatever the system is now. I don't know. I mean, so this is, but don't neglect that, because this is very fundamental of mathematics. If you're really into basic sciences, you should I mean, you should be able to because this what gives you the framework of mathematical language. This is how a mathematician speaks, and the mathematics is the language of science.
So one question from Ayushman is,
Okay, thank you.
thank you, sir, thank you. One question from Ayushman is, what if two planets in our solar system collide? Do you mean? Okay, so what if they collide, and will there be any? No, not really. Two planets, they don't have gravitational potentials strong enough to warrant some study in a higher dimension or an extra dimension. You don't really have to study that in higher order, higher dimensional theories. You can explain them very clearly using three-dimensional theories when two planets collide, and it's basically just an explosion and tidal disruption and stuff like that because of rotation and the proximity to a very strong gravitational source, which is our sun. So that's basically it, actually, Ayushman. Advait Joshi, whether different pulsars have different radiation. They do. They have different, so radiation values, I'll put more light into it. They do have different luminosities. The luminosity is determined by how massive the star is, how big it is, and how young or old it is. Also, how fast is it rotating? So all these things contribute to different types of radiation that you observe from the pulsar, how strong its magnetic field is as well. So all these things, yes, you were right, they have different values. How did life start on Earth? As when Earth evolved for around 500 million years, there was no life, but then how did life suddenly arise in Earth? Suddenly, I don't really know, but it's usually evolution of carbons and hydrocarbons in our atmosphere. That's how life started, but I'm really not an expert on planetary sciences, so I cannot answer that in more detail. Another one by Shobhankar is, can you explain the string theory in details? Oh, wow. So that's a question for Saswato. He's very closely, his work is closely related to strings, actually, so he understands that a bit better. Saswato, can you go ahead? As details as you can. I mean, as too many details, of course.
Yeah, of course. I myself am not expert in string theory, but it's closely related to. So at present, when we try to explain something, like explain some laws of physics, for example, when you study Newton's law, we force equal to mass into acceleration. We are always talking about a point object. So you have a point which has some mass, we push it. Now you might say that now we go into rigid body dynamics, so it's an extended object. But again, we work as if there are a lot of points which are related to each other in some way, and each of this point has some characteristic. For example, distance, or it has some coordinate like distance, rotational velocity, something. So every So what I mean to say is that everything is characterized by a point. Now, if you go further into quantum mechanics, still evolution or like quantum mechanical treatment of a point. Now, string theory is like that instead of a point, now a fundamental object is a string. By string at a microscopic string, which is 10 raised to the power minus 33 centimeters small, it's known as a Planck length, and it's a fundamental length of the universe. So now now this fundamental object is string. So it means that you have two objects, like you now have two coordinates related to some fundamental object. So now what a string can do, a string can be closed, a string can be closed, string can be open. So now has anyone of you played guitar? So you might know the string vibrates, and I think I'm not sure, but in 11th, 12th, you might have studied about standing waves. So there are different modes of vibration, like different frequencies. There's a fundamental frequency of each length of string. So now this string might have different fundamental frequencies, and every excitation, every frequency is relates to some interaction, some force. So this is like the extreme basic foundational principle of string theory. Now to string theory to exist, we need for different technical reasons, which is way beyond the scope of even for a bachelor student, is that it needs 11 dimensions for some reason, 26 dimensions or 11 dimensions in some particular cases. And but the fundamental thing is that excitations of the string. Now this was the basic, this was I think 60s, 70s. At this moment, it's not even strings. We work in d-dimensional membranes. So now, string, next thing is like a sheet. Sheet is, the scientific word is membrane. Now we go, as we are in higher dimensions, it's known as a D-brane. So it's, of course, you can't, visualizing is a little bit difficult, but it's a n-dimensional or d-dimensional equivalent of a membrane. So just to make a little bit things clear, in a two-dimensional world, for example, someone lives on on its tabletop. They live on a tabletop. They don't have extension. It's just a point on a tabletop. So for them, a line, one-dimensional object is a membrane. For me, a two-dimensional surface of the sheet of paper is a membrane. For a four-dimensional person, a three-dimensional, maybe sphere is a membrane. The same. So if you live in 11 dimensions, then we have a 10-dimensional membrane. So this is the definition of a membrane. So this is how interactions are described. Anything else, like follow-up questions? And I think it would be better if you don't ask in chat. You can just unmute and ask.
Yeah, so basically that's string theory in detail, but I'm not really an expert on string theory, but basically a very simple analogy is just having strings of a guitar, and you play different notes on the guitar, and each of those notes corresponds to a different fundamental particle, which in turn makes up the universe. So it's just a way of describing things.
The word theory is a little bit of a misnomer, by means that you might think it's not one theory.
Yeah,
it's a framework. It's a framework to describe our world. So there's a subtle difference between a framework and theory. So you can have some descriptions which has nothing to do with our universe. But I can say that for example, one mode of this guitar or one mode of this string corresponds to maybe say gravity or maybe electromagnetism. Then it's a particular string theory relevant to our universe.
Yes.
So each of this mode relates, or each of these excitations or each of these configurations relate to one single theory. Itself, string theory is a framework.
Yep.
I think there's another question which is also more closer to me is...
but I'll try and answer a private question first. It said, what do you think when a person becomes successful? Everyone has different meanings to success. So success means to me, okay. To me personally, it's just, I don't know. For me, success basically is still being connected to family and friends. being happy about what I do, and at the end of the day, being able to sit back and realize that what I did that day was something that I wanted to do, not that I was forced to do. So that's basically what success means to me. And yeah, so that's basically it. Rather than material success, I think this is much more important than that. Another question from Advait Joshi was, if something goes inside the black hole, after that, where it goes? Okay, so Saswata here is actually actively working on black holes, so he can answer that. Let's answer it from a classical perspective. So very basic classical perspective.
I mean, so in classical perspective, what's a black hole? So black hole is an area of strong gravity where even light cannot escape. So inside a black hole, I mean, if light cannot escape, you cannot send information. So it means that something is stuck. But this is a classical approach. I mean, this doesn't take into account what happens at small scales. So I think, and this is what Hawking imagined, like Stephen Hawking imagined. Now, for example, if you have a surface of a black hole, there are some small particles. For example, like electron-positron pair in vacuum. So just to make sure that there is spontaneous production of particles in vacuum in universe. What it means is that if some parameter, for example, charge and energy is conserved, you can have spontaneous production, nothing can stop it. So if there is an electron-positron pair, which means that electron and positron both have the same mass, and they have they have opposite charge, so your total charge at that place is conserved. So you can have that kind of thing. So if that happens near the boundary of a black hole, this and there's a point in black hole which is event horizon, after which information cannot escape. So there's a spontaneous production, and this one electron gets sucked into the black hole, and then now with conservation of momentum, so there's a huge momentum which gets sucked inside, the proton gets shot away, and positron gets shot away, and other way around. So he imagined that in some mechanism this information can escape. So now this electron and positron are connected in something known as quantum entanglement and everything. So there is some escape of information. Also, because now gravity, now we again go back to classical perspective. So you know that gravitation has an acceleration, right? I mean, you drop an apple, it accelerates. When it accelerates, there is some force involved, some energy involved. Now, in general relativity, it's a curvature. So any kind of curved surface means there is some kind of acceleration. So when you do like quantum mechanics on a curved surface, there would be like some loss of energy. I mean, these are all related. So this is somehow information gets lost, and this is related by the black hole thermodynamics. And so this means that black hole has some temperature, and by temperature it means radiates, but the temperature is so low and the rate of radiation is so small that you are going to lose information in some such a way. So this is what is this is the rough picture we have, and unfortunately this is the rough picture we actually everyone scientists have. So this one of my future aims to actually understand how things escape from black hole. This is an open problem in physics. We don't know completely yet. We know somewhat what's happening. We have some mathematical ideas, some concrete ideas to explore, but we really don't know.
Yeah. So as Saswata said, from a very astrophysical perspective, a black hole is nothing but just the fate of a star. It's a dead star of a certain very high mass, because of which the gravitational self-collapse or the self-gravity is so strong that no kind of external pressure can sustain the structure of the star. So what happens is that it collapses and forms a very deep curvature in space-time. Now, from mathematically, we can only, from the general theory of relativity and other similar theories, we only have information about certain ranges to a black hole. So we have information till say the event horizon and then stuff like that. Beyond that, we can't really estimate what happens. There are models and kind of different ideas that say there's a white hole and all these kinds of things, but you can't really have concrete information about that. So you can't really say that this is what happens or that is what happens. Okay, so ma'am has said that.
Okay, just before we go to that question, sorry. So this is perspective of one of my supervisor here. So now, I mean, you suck all the air into one corner of your room, right? And then you let it go. So when you suck it in one corner, you can really count what's happening. Like you can count each molecule, and I mean it's easier to do that, so it's related. Now you let it spread in the room. After some time, it's all over the room, and now each of them is spread everywhere. So this process is known as thermalization, or rather, which means that you come into an equilibrium, or like it's in a basic state. So this is something what happens with a black hole too. So matter gets sucked into a place, and now this is now with these mechanisms I described, this is getting like thermalized, or this is getting outside in the universe. So you can say that this is something of an analogy like that, but it's a personal perspective, and this can be challenged by maybe other scientists. But this is something like that. You take air molecules into one corner and let it spread again. It's something like that. I mean, I think like I might not have made anything clear, but may have caused even more doubts, and that kind of is my purpose, so that you get you get inspired to actually study these things on your own.
That's true. So, ma'am has asked to talk a little bit about approaching physics in the right perspective and in terms of the career and everything. Okay. So, physics again should never be overcomplicated. Don't overcomplicate physics. Don't go into absolute details from the very beginning. Keep your fundamentals as crisp, as clear as possible. That's the main thing. Read good books. Read very basic books. I'll try and send a list of books to ma'am, if possible, and then she can share a drive or something where I'll send PDFs. It's very important to keep your fundamentals clear. That's the most important thing. It doesn't matter how much detailed information you have about something, but it's very dangerous to have wrong or half information about something. So it's very important that you have your fundamentals clear. For a career, from a career perspective, the first thing that you have to know is that nothing is unachievable. So you should not think about some person who is studying or working in Europe or America, for that matter, to think that they are somewhat at a different level, and that's unachievable. One of the ideas of me doing this public outreach is to make you understand that I am one of you, obviously, and people that I work with here, we are all just scientists, which anyone can be actually. Anyone can be a researcher, or anyone for that matter. So and we encourage people to connect with us, to send us emails, find, say you have an interest in a certain project, start finding people, scientists at different institutions who are working in that project. Try to look up at research papers on archive, practice those things. Same, please write the links of archive and ResearchGate and all these things on the chat. So these are some of the things that you should practice from the very beginning. Reading research papers of the interested projects for you, and then you'll find information about who the authors are. If you know who the authors are, you can connect to them. You can email them, cold email them. They might not reply to you in the beginning, but stay on it. Keep sending follow-up emails. Ask them about what kind of work is exciting for them currently, and if the project that you are interested in is something that is interesting for him as well, and if you would like to collaborate, ask these questions. At what capacity? Ask these questions. So that's something very important, to keep asking questions, keep connecting to people. For coming abroad and for education, if you want to come at the bachelor's level, the only thing that you have to do is, for America, you have to go through SATs. You have to give SAT exams. The SAT scores usually help in selecting universities in America. For Europe, one problem in the bachelor's is that you usually have to learn the language of which country you are going to study in. So if you're going to study in Germany, you have to speak Deutsch. If you're going to Netherlands, you have to study Dutch, only for the bachelor's though, and in some courses. But after the bachelor's education, when you apply for MSc programs, then it's English all over the world. So it doesn't matter where you are, in Spain, in Italy, in Germany, Netherlands, it doesn't matter. In America for that matter. So there are different scholarships that you can apply to. For me, I did my master's in Germany, so I know that in Germany, education is basically free. You don't really have to pay enormous amounts of fees for that. And you can get scholarships through different entities. There's DAAD, D-A-A-D, that's a scholarship entity for Germany. Then there are Commonwealth scholarships, Erasmus scholarships, lots of scholarship programs. So you can just Google scholarship programs for abroad for master's levels, and they'll show you numerous examples. So one thing that you have to keep in mind is try and get as much research experience at a young age as possible. Try to work with people on very short projects, like 2-month projects, 1-month projects, that's fine. Try yourself, like do very small projects with different teachers. Start from your teachers, in fact. Ask your teachers. Ask your physics teacher, chemistry teacher, biotechnology teacher. Ask them, like, could you work with me for a very short project, like a month project or a 2-month project? It can be very simple, something very simple. And try to go through that entire process as to selecting a project, then trying to define the framework of that project within which you can work on. And then at the end, developing a project report, writing a project report and submitting it. So go through that whole process on small scales, like 1 month, 2 months, short projects. That would help you enormously because that's basically all that we do, obviously on longer scales, but that's basically all that you do. Yeah, that's basically it. For PhDs, it's the same thing. What I did when I applied was just go through ads at different websites, and I just started talking to people. I did not care about which university I do it in, and I did not care about the name of the institution that I would work in. But only the person that I wanted to work with, because that's more important. Because in science, even as a student, the working capacity is mostly like you work like a colleague to that person. So that person has to want to work with you. So you have to be very positive. You have to bring a positive impression along with you. And that's basically all that matters. So yeah, so the key takeaway point is to read the basic books, keep your basics clear, and start connecting to people as soon as possible. Start getting experience as soon as possible. Okay.
To add something else to that, this is something we have talked about again and again, is that there are certain myths, or rather there are certain misinterpretations of some quotes which get into the heads of young students, is that mathematics and physics are independent.
No, they're not.
This is what happens is that some people, like this is quotes by, I mean, great scientists Feynman and Stephen Hawking, is that they say that mathematics and physics are independent, which means that like physics is different and mathematics is, I mean, the interpretation what happens is that physics is different, mathematics is different. No, what they mean by saying is that you don't need to be an expert in mathematics to be a physicist, or you don't need to be an expert in physics to be a mathematician. But when you study physics, you have to understand that your physical concepts are translated into mathematical languages. So of course, there's a physics element, like what are we going to study? Why are we even studying? That doesn't need mathematics, but to actually give it concrete results, you need to are able to understand the mathematical concepts. So to be if you want to study physics, always have this ability to map English to maths. The concepts to maths, like for example, gravity. I mean, this is a little bit advanced. Like if gravity is curvature, then why it is related to some mathematical quantity, or why it is something like that. So this connection should be understood. Like this concrete mathematical thing, concrete mathematical concepts with the English version or the language version you have. So this is very important, and this. I mean, I personally have faced this problem because I was teaching general relativity as a teaching assistant last term, and people do ask this kind of question. Like, but I want to understand the physics, but not the mathematics. No, you can't do that.
Okay, so how does someone ask something? But okay, it's removed. How does a cycle pump work? Oh, okay, cycle pump. Okay, I just have a basic idea. It's just basically I think they take in air, and there's a chamber where they can store air temporarily in an ad hoc manner, and then there's another chamber where that air that was taken in is carried into, and that in the second chamber there's something that causes compression of that air. So it can be electrical compression, mechanical compression, which you do yourself with your hand, like a small pump or a big one, or an electrical compression, any kind of thing. So it just compresses the air, and the compressed air goes through a pipe, through a valve, which usually is closed, but the force of the compression causes the valve to open, and then it goes in the tires. That's basically all I know. But okay, one more question. I think Sashwata would be better answering this. Why do boson particles don't have any mass? Okay, what is the role of graviton in quantum physics? Okay, the role of graviton in quantum physics, you can answer that.
So this is straight to home actually. No, bosons. There's nothing to do with bosons. Can have mass. There can be massive bosons. There are massive bosons. For example, for fundamental interactions, you have electromagnetism, you have weak interaction, you have strong interaction, and you have gravity. Strong interaction and gravity and electromagnetism are propagated by massless bosons, but your weak interaction has mass. It's a massive your I mean those are propagated by what is known as Z and W bosons. They are massive. So bosons can have mass. There are different ways of mass generation, which I don't want to go at this moment. It's a little bit more advanced, but it can have mass. And what was the second question?
Tell them just a little bit basic definition about what a graviton is.
I mean, it's exactly like photon. I mean, photon is the unit of electromagnetic interaction. I mean, when there's an electromagnetic interaction, two particles exchange photons. So exactly when there is a gravitational interaction, for example, interaction between me and the Earth, we are exchanging gravitons. It's nothing. I mean, there is nothing too profound about it. It's just the unit of and we even don't know if it's basic or not. I mean, if it's like I would just add like if it's a fundamental interaction or not. This is also, I mean, in a lot of books you would study that there are 4 fundamental interactions, but you have to take this with a pinch of salt. We even don't know if there are 4 fundamental interactions or there are 100 fundamental interactions. This is this is the limited understanding of like human understanding is that there are 4 fundamental interactions, and this is something like that. So for electromagnetism, it's photon. For nuclear forces, it's gluon. For weak interaction, it's W and Z bosons, and for gravity, it's graviton. Simple.
Okay, and so when I've seen some of the questions that talked about exotic objects, or phenomena like string theory and stuff like that. Wormholes and all these things. So one thing we have to know that when we develop physical theories using mathematical models and also using mathematics, we always, when we talk about something as an entity, as a physical entity or a phenomena, we usually try to validate them or wait for them to be validated by observations. So we need observational evidence to have concrete information about a theory so that we can talk about it, right? So even the black hole was only a theoretical concept till about 5 years ago. It was a very valid one. It was constrained by several mathematical models, and there are certain uniqueness aspects to the theories that definitely told us that black holes do exist, but then it was only validated by the detection of gravitational waves, for example, in 2015. Whereas Einstein did those calculations in 1915. So that was 100 years later. So we always have to wait a little bit more for observational evidences because they depend on technicalities and stuff like that. You must have seen the recent image of a black hole that actually gives you more information about what it may be like. So then Yeah, so these things come about. So whenever we talk about exotic things or phenomena, we have to try and find valid solutions through observational evidences. So, any question?
I mean, I would just add to this answer is that there was a question about what is beyond universe, right? So just to add to it, like when we talk about these exotic phenomena, for example, even if we know about some object which doesn't exist, but it might have some fundamental observational consequences. Like, for example, existence of black holes was very necessary for, is a consequence of the same theory which gives us how a GPS would work, and GPS is definitely work. So, I mean, these are kind of things which gives you a clue that this object must be there. Even though you cannot see it, or even if you don't have the technology, you are very sure of that, because this has some other consequences which are much more concrete. Other question.
Dipto, I think you and Shashwata have literally answered every question that has been posted in the chat or asked to you guys directly. Now I request Haripada sir, Principal KV IIT. Sir, could you kindly speak a few words on this occasion, please?
Okay. Learned Mrs. Ramia, PGT Biology of KV IIT Guwahati, Uddipta Ji and Shashwat Ji. Really, it is a matter of great pleasure for all of us to have the opportunity of interaction with you and our student, and also with our teachers. I can see two of my teachers have joined. Madam Ramia is there. Also, Madam Miranda has also joined. I'm not sure that she is still online or not. So it is a, once again I want to mention that it is really a matter of great pleasure and very good opportunity for all of us to know that you were KVN and you are doing very wonderful job, and also you are working for the students in India. I think it is a very good gesture, and I remind your answer of being successful to you. You have beautifully answered the question. Actually, success is nothing but capable of doing what you want to do. Very, I like the answer very much.
Thank you.
Success is nothing but ability to be connected with your relatives, with friends, your basically the place, the people you were connected to. Very good answer, and I think all of our students will certainly note it down that being successful is not only earning too much of money. Yeah, I think in the morning also, or in a few days back, I was discussing. I was in staff meeting or somewhere else. I have the same feeling that it is not that earning too much of money is being successful. We have to be successful. We need money, but that money is not everything. We have to contribute for our society, and before we can contribute for the society, we have to contribute for ourselves. We have to identify ourselves. We have to know ourselves, and then we can think of our family, our country, the whole world. So, thank you, Uddipta. Thank you, Shashwat ji. Thank you, Romeo madam, for conducting this session for our student. I think student will be motivated. They will be working on right direction. They will be in touch with you for getting feedback to be successful in life, to be a physician, to be connected with their uh, relatives, with their teachers, with their friends, and they will get in touch with you for being successful. Thanks to one and all.
Thank you very much, sir. Definitely. I'd like to add a short thing. So I'm doing this this public outreach thing. Basically, I started this with my alma mater, KV Borpeta and KV Khanapara. And as Rama ma'am has such a, she has a big hand in my research career. So I'd always be grateful to her, and I thank her for giving me this opportunity. I've talked about what I do here in my institute as well to scientists of different at different stages of their career. There are master students, even assistant professors and professors who are working here, who would also like to give talks to you guys at some time. So please let me know if you'd like to hear more of these talks. This is, once again, I stress this, it's a wonderful opportunity when you get to talk to people that are working at different fields and get an idea of what kind of work goes on in different fields. So yeah, and I thank you all for coming. I'd hand it over to ma'am.
Thank you, Dee, and thank you, Shashwata. Really to come to the level of every student who is present over here and answer the questions so beautifully in a way that they could understand. And most importantly, I salute your attitude, to find time to reach out to the students and make a difference. And as Sir was rightly saying, seize the opportunity to say, I loved your definition of success today. I feel so proud listening to it, After all these years, after achieving so much, you're so grounded. Thank you so much for being you, Loved it.
Thank you, ma'am.
And thank you each and everyone who is present over here, all my children. Thank you so much. It was really, really nice interaction. I hope we can have many more such
Oh, cut off, I think. Well,
I think there was some connection issues.
but that's all right. We can wait.
Yes, okay. On behalf of Ramya madam, I once again convey my heartfelt thanks to both of you, and also to all my student and Ramya madam for conducting this program, this interaction session. I know that after this interaction, the students who have participated and the student who could not participate will be recharged with some kind of energy. They will be putting their energy towards right direction, towards the path of success. Thank you one and all.
Thank you, sir. Thank you, students. Thank you, everyone.
Okay.
Thank you. Thank you, everyone. Bye-bye.
Sorry, got disconnected, but I hope I conveyed everything, on behalf of everyone. Thank you so much, Shashwata. Thank you so much. It was great knowing you,
It's a pleasure.
and we hope to have many more fruitful interactions. Okay, and thank you, everyone. Thank you, all the children who participated in this session.
Thank you.
Thank you.
Thank you, ma'am. Everyone. Bye-bye.
Bye.
Bye, Dee. Bye. Bye.